When installing a 30 amp panel in a shed located 80 feet from the main house, proper grounding is crucial. Given the shallow ledge, achieving adequate grounding requires careful consideration of the number, spacing, and connection of ground rods. For a 30 amp panel, the National Electrical Code, or NEC, requires a minimum of 2 ground rods. However, soil conditions can significantly impact grounding effectiveness. Poor soil conductivity may necessitate additional ground rods to achieve the required resistance to ground. The ideal spacing between ground rods is typically between 6 and 10 feet. Since the ledge is only 3 feet below the surface, you'll need to adjust the spacing accordingly. A spacing of 3 to 5 feet between the ground rods is recommended in this situation. This closer spacing helps compensate for the limited depth. The NEC mandates that ground rods be connected in parallel. To ensure a reliable and safe connection, use insulated copper wire that is at least number 8 American wire gauge, or AUG, in size. Securely join the wires together using a grounding lug or an appropriate splice connector. This parallel connection provides multiple paths to ground, enhancing safety and minimizing impedance. After installing the initial 2 ground rods, it's essential to measure the resistance to ground. The NEC requires a resistance of 25 ohms or less. Use a ground resistance tester to perform this measurement. If the resistance exceeds 25 ohms, you'll need to install additional ground rods. When adding ground rods, install them perpendicular to the existing rods. Maintain the same spacing, 3 to 5 feet in this case, and use the same connection method. Remeasure the resistance after each additional rod installation until you achieve the desired 25 ohms or less. Remember to follow these steps. Firstly, install 2 ground rods spaced 3 to 5 feet apart, ensuring they are parallel to each other. Secondly, measure the resistance between the ground rods using a ground resistance tester. Thirdly, if the resistance is below 25 ohms, you have achieved an acceptable ground. Fourthly, if the resistance is too high, install additional rods perpendicular to the existing rods. Fifthly, remeasure the resistance after each additional rod installation. Sixthly, repeat steps 4 and 5 until the resistance is below 25 ohms. Seventhly, once all ground rods are installed and connected, terminate the ground wire from the panel to the grounding lug or splice connector. Throughout the grounding process, be aware of local electrical codes and inspector requirements. Your local electrical inspector may have specific guidelines regarding the number, spacing, and connection of ground rods. It's always advisable to consult with the inspector before commencing the installation to ensure compliance with all applicable regulations. Grounding rod installation involves several crucial elements. Firstly, material selection. Ground rods are commonly made of copper-clad steel or stainless steel. Copper-clad steel rods offer a good balance of conductivity and corrosion resistance, while stainless steel rods are suitable for highly corrosive environments. Secondly, driving depth. The NEC requires that ground rods be driven into the earth to a minimum depth of 8 feet unless rock bottom is encountered. In your situation, because of the ledge being at 3 feet depth, you will need to consider that you may not be able to drive an 8-foot rod. Thirdly, conductor size. The grounding electrode conductor, or GEC, which connects the ground rods to the electrical panel, must be sized appropriately based on the size of the service entrance conductors. For a 30 amp panel, a number 8 AWG copper conductor is typically sufficient, but it's essential to consult the NEC or a qualified electrician to determine the correct size. Fourthly, connection methods. The connection between the GC and the ground rods must be made using approved connectors or clamps that are listed for direct burial. These connectors should be made of corrosion-resistant materials to ensure long-term reliability. Fifthly, protection from damage. The portion of the GEC that is exposed to physical damage should be protected by conduit or other approved means. This is particularly important where the GEC exits the ground and enters the electrical panel. Sixthly, continuous run. The GEC should be run in one continuous length without splices or joints except where unavoidable. Any splices or joints must be made using approved methods such as exothermic welding or listed splice connectors. Seventhly, identification. The GEC must be clearly identified along its entire length, typically by green insulation or by marking it with green tape. This helps to distinguish it from other conductors in the electrical system. Eighthly, bonding. All metal enclosures, such as the electrical panel and any metal conduits, must be bonded together to create a low-impedance ground fault current path. This bonding helps to ensure that any fault currents are safely conducted back to the source, tripping the circuit breaker and preventing electrical shock. Ninthly, testing. After the grounding system is installed, it's essential to test its effectiveness using a ground resistance tester. This test measures the resistance between the grounding electrode and the earth, providing an indication of the overall grounding system performance. 10thly, documentation. Keep a record of the grounding system installation, including the number, size, and location of ground rods, as well as the results of any testing. This documentation can be useful for future maintenance and troubleshooting. The grounding system is a critical component of any electrical installation, and it plays a vital role in protecting people and equipment from electrical shock and damage. By following the NEC requirements and best practices, you can ensure that your grounding system is safe, reliable, and effective. Soil composition can significantly impact the effectiveness of a grounding system. Different types of soil have varying levels of conductivity, which affects how well the ground rods can dissipate fault currents. Sandy soils, for example, tend to have poor conductivity due to their low moisture content and large particle size. This can make it difficult to achieve the required resistance to ground, and may necessitate the installation of additional ground rods or the use of soil amendments to improve conductivity. Clay soils, on the other hand, generally have better conductivity due to their higher moisture content and smaller particle size. However, clay soils can also be prone to corrosion, which can degrade the ground rods and reduce their effectiveness over time. Rocky soils can also pose challenges for grounding, as it may be difficult to drive the ground rods to the required depth. In these situations, it may be necessary to use shorter ground rods or to install the ground rods horizontally in a trench. Soil moisture is another important factor that affects grounding effectiveness. Moist soil is a better conductor of electricity than dry soil, so it's important to ensure that the ground rods are installed in an area where the soil remains consistently moist. This can be achieved by locating the ground rods near a water source, such as a downspout or a sprinkler system, or by using soil amendments that retain moisture. Soil temperature can also affect grounding effectiveness. Cold soil is a poorer conductor of electricity than warm soil, so grounding systems may be less effective in cold climates. In these situations, it may be necessary to install additional ground rods or to use soil heating cables to keep the soil around the ground rods warm. Soil pH can also affect the corrosion rate of ground rods. Acidic soils can accelerate corrosion, while alkaline soils can slow it down. In areas with acidic soils, it may be necessary to use stainless steel ground rods or to apply a protective coating to the ground rods to prevent corrosion. Soil contamination can also affect grounding effectiveness. Contaminants such as salt, chemicals, and oil can reduce the conductivity of the soil and increase the corrosion rate of ground rods. In areas with contaminated soils, it may be necessary to remove the contaminated soil and replace it with clean soil, or to use specialized grounding techniques that are designed for contaminated environments. To ensure that your grounding system is effective, it's important to consider the soil conditions in your area and to select the appropriate grounding materials and techniques. You may also want to consult with a qualified electrician or grounding specialist who can assess your soil conditions and recommend the best grounding solution for your needs. Understanding grounding principles is essential for ensuring electrical safety. Grounding provides a low impedance path for fault currents to return to the source, tripping the circuit breaker and preventing electrical shock. The NEC specifies the requirements for grounding electrical systems to protect people and equipment from electrical hazards. One important aspect of grounding is the concept of impedance. Impedance is the total opposition to current flow in an alternating current, or AC, circuit. It includes resistance, which is the opposition to current flow due to the material of the conductor, and reactance, which is the opposition to current flow due to the inductance and capacitance of the circuit. A good grounding system should have low impedance to ensure that fault currents can flow quickly and easily back to the source. This helps to trip the circuit breaker and prevent electrical shock. Another important concept is bonding. Bonding is the process of connecting all metal enclosures, such as electrical panels, conduits, and equipment, together to create a low impedance ground fault current path. This bonding helps to ensure that any fault currents are safely conducted back to the source, tripping the circuit breaker and preventing electrical shock. The grounding electrode system is the primary means of grounding an electrical system. It consists of one or more grounding electrodes, such as ground rods, ground plates, or underground metal water pipes, that are connected to the earth. The grounding electrode system provides a low impedance path for fault currents to dissipate into the earth. The grounding electrode conductor, or GEC, is the conductor that connects the grounding electrode system to the electrical panel. The GC must be sized appropriately based on the size of the service entrance conductors. The equipment grounding conductor, or EG, is the conductor that connects the metal enclosures of electrical equipment to the grounding system. The EGC provides a low impedance path for fault currents to flow back to the source, tripping the circuit breaker and preventing electrical shock. Ground fault circuit interrupters, or GFCIs, are devices that detect ground faults and interrupt the circuit to prevent electrical shock. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas, where there is a high risk of electrical shock. Surge protective devices, or SPDs, are devices that protect electrical equipment from voltage surges caused by lightning strikes or other events. SPD divert the surge current to ground, preventing it from damaging sensitive electronic equipment. Electrical inspections are an important part of ensuring electrical safety. Electrical inspectors check to make sure that electrical systems are installed in accordance with the NEC and other applicable codes and standards. If you are planning to install a new electrical system or make changes to an existing system, it's important to obtain the necessary permits and have the work inspected by a qualified electrical inspector. Grounding is a complex topic, but it's essential for ensuring electrical safety. By understanding the principles of grounding and following the NEC requirements, you can protect yourself and your family from electrical hazards. Here are some additional considerations for your specific situation. Firstly, soil resistivity. Soil resistivity is a measure of how well the soil conducts electricity. Low soil resistivity is desirable for grounding systems, as it allows fault currents to dissipate more easily into the earth. You can measure soil resistivity using a soil resistivity meter. Secondly, ground enhancement materials. Ground enhancement materials are substances that are added to the soil to improve its conductivity. These materials can be used to reduce the resistance to ground and improve the performance of the grounding system. Thirdly, exothermic welding. Exothermic welding is a method of joining conductors together using a chemical reaction that generates heat. Exothermic welds are very strong and corrosion resistant, making them ideal for grounding connections. Fourthly, concrete encased electrode. A concrete encased electrode is a grounding electrode that is encased in concrete. Concrete encased electrodes are often used in new construction because they provide a very low impedance path to ground. Fifthly, underground metallic water pipe. An underground metallic water pipe can be used as a grounding electrode if it is in direct contact with the earth for at least 10 feet. Sixthly, structural metal. The metal frame of a building can be used as a grounding electrode if it is effectively grounded. Seventhly, local amendment. It's important to check with your local building department or electrical inspector to see if there are any local amendments to the NEC that may affect your grounding system. Eighthly, qualified electrician. If you are not comfortable working with electrical systems, it's best to hire a qualified electrician to install your grounding system. An electrician can ensure that the system is installed correctly and safely. Remember, when measuring the resistance of the ground rods, disconnect the ground wire from the panel. Using a ground resistance tester, follow the manufacturer's instructions to perform the measurement. Also, Ensure that the ground rod clamps and connectors used are listed for burial. These connectors are typically made of copper or bronze and are designed to withstand corrosion in the soil. Additionally, when installing the ground rods, consider using a ground rod driver. A ground rod driver is a tool that makes it easier to drive the ground rods into the ground. It can be particularly helpful in rocky or hard soil. To minimize the risk of damaging underground utilities, always call your local one-call center, such as 811, before digging. This will help you identify the location of any underground utilities and avoid damaging them. If you are using multiple ground rods, it's important to ensure that they are all connected together with a continuous grounding electrode conductor. This conductor should be sized according to the NEC and should be securely connected to each ground rod with listed connectors. If you are using a metal water pipe as a grounding electrode, it's important to ensure that the pipe is electrically continuous and that it is in direct contact with the earth for at least 10 feet. You should also bond the water pipe to the electrical panel with a grounding electrode conductor. In some cases, it may be necessary to use a combination of grounding electrodes, such as ground rods and a metal water pipe, to achieve the required resistance to ground. The type and number of grounding electrodes will depend on the soil conditions, the size of the electrical system, and the requirements of the NEC. Finally, remember that grounding is an important safety measure that can protect people and equipment from electrical shock and damage. By following the NEC requirements and best practices, you can ensure that your grounding system is safe, reliable, and effective. It is recommended that you consult a qualified electrician.